Here are our video notes for gas stoichiometry. So just remember that stoichiometry is the mass relationship between reactants and products in a chemical reaction. And in general, we want to follow these rules when using stoichiometry in our gas law unit. So we want to do stoichiometry to do molar mass conversions, and then we want to utilize the ideal gas law, which is, remember, our pivnert, to convert between moles and volume. So we're going to use stoichiometry and the ideal gas law, or stoichiometry and the combined gas law, and I'll show you how to do that later in terms of when we're doing stoichiometry with our gas law unit. So don't think that it's just going to be one thing. You can use stoichiometry and the ideal gas law to answer a question. So for example here, where we're going to use stoichiometry and the ideal gas law, on this problem it says how many grams of calcium carbonate must be decomposed to produce 5 liters of carbon dioxide at STP. And remember, here's an important thing at STP, so I know I'm able to use my gas stoichiometry. And so the first thing it says is I'm going to use pivnert, or PV equals nRT, to solve for my n value. So understand that this is a very high-level question, and the reason why we're doing this on our notes together is I want you to be able to go back and reference it. So one of the things that you need to see is that it says how many grams of calcium carbonate must be decomposed to produce 5 liters of carbon dioxide. So the minute that you see you've got grams of calcium carbonate and liters of carbon dioxide, you know you need to do a couple of steps. So the first one on this one is because I'm given liters, I need to solve for moles. And so I use pivnert, and I'm going to solve for moles, but when I do that, it's going to be moles of carbon dioxide. So when I solve, I'm going to get that I have 0.223 moles of carbon dioxide. So I was able to plug in all my values because I'm at STP, so I know 1 atmosphere is at STP. 5 liters was given in the problem. N is my value I'm trying to solve for. 0.0821 is my known value, that's our constant of R. And then 273 Kelvin is also STP. So if you're wondering where I got those values, STP can tell me a lot of information. It tells me atmospheres, it tells me Kelvin, and then I know it helps me remember that my R is 0.0821. So I'm solving for N here, but this is moles of carbon dioxide, and my problem asks me for grams of calcium carbonate. So now you simply do stoichiometry. So you start with, when we're talking about this, now you start with 0.223 moles of carbon dioxide and do stoichiometry to grams of calcium carbonate. So now as we look here, just like normal, if I've got moles of carbon dioxide here, I know that down here the unit that needs to go down there is moles of carbon dioxide in order for it to cross out. And then I ask myself, can I go from moles of carbon dioxide to grams of calcium carbonate? I cannot, so I need to go to moles of calcium carbonate. And remember, I'm in Mole City, and my map to Mole City is the chemical equation right up here. And so it looks like I have a 1-to-1 ratio. So then I ask myself, am I done? Moles of calcium carbonate is what it's trying to get, is what I'm in right now, and I'm trying to get to grams of calcium carbonate. So I'm not done. So I need to go ahead and do another T-chart here. So now I have moles of calcium carbonate on the bottom, and I can indeed go to grams of calcium carbonate. I know that 1 mole is equal to 100 grams. So I know that 5 liters of carbon dioxide at STP needs to use 22.3 grams of calcium carbonate. So I'm able to answer my problem here where I'm asking how many grams of calcium carbonate must be decomposed. I would need 22.3 grams of calcium carbonate. So there's one example of using the ideal gas law first and then using stoichiometry. And then the next one is going to be an example of using stoichiometry first and then using the ideal gas law. So here we've got calculate the volume of hydrogen gas that can be obtained under laboratory conditions of temperature and pressure of 25 degrees Celsius and 0.9 atmospheres when 5 grams of sodium is reacted with water. So what I'm going to do here first is actually take the grams of sodium and I'm going to figure out how many moles I have. And the reason why I do that is when I look at my PV equals nRT, when I set that up, I know that pressure is 0.9 atmospheres. I know that volume is what I'm trying to find, but I also don't know N, but I'm given the information of mass. So because I don't know N, but I'm given the 5 grams, I actually can do stoichiometry to help me figure out N. So I really only have one variable, and I know that my R is 0.0821, and then I know that my temperature is 25 degrees Celsius, and I need it to be converted to Kelvin, so I add 273. So my first step is going to be take that 5 grams of sodium and do stoichiometry. So I'm going to put grams of sodium on the bottom. I'm going to moles of sodium. So what do I want to take this to? Do I want to stop at moles of sodium, or do I want to look at moles of hydrogen? Well, because I'm actually asked to calculate the volume of hydrogen, I want to take this stoichiometry t-chart all the way to moles of hydrogen, because if I were to answer it in moles of sodium, that's not going to help me with the value that I need at the end. So my stoichiometry here is actually going to end up going to moles of hydrogen, and I find my mole ratio there, the 2-to-1, from my balanced chemical formula, which is down here. So now I've solved for my moles of hydrogen, and I can plug that back in over here in my PV equals nRT equation. I can go ahead and set up my algebraic equation and plug in my variables and solve for volume. So I know that the volume of hydrogen gas that can be obtained under laboratory conditions with those values is 2.95 liters of hydrogen gas. So there's just an example, like we talked about in our first slide, of needing to use the ideal gas law and stoichiometry in order to be successful here. All right, I'm going to stop the video, and I'll start in the next video with these notes to explain Avogadro's law and using the combined gas law or the ideal gas law with gas stoichiometry.